Hello, Physics 1 students. My name is Ben, and I am one of your Physics 1 LAs. Welcome to Virtual Lab. Today in Virtual Lab, we are going to be talking about the terminal velocity of an object in free fall. For the purpose of this experiment, our object is going to be coffee filters. Why coffee filters, you might ask? Because they are very lightweight and they reach terminal velocity very quickly. For this experiment, you will be holding the coffee filter up high and releasing it and calculating its terminal velocity on the way down. Unfortunately, we cannot calculate velocity as we would like, but we can do it a different way. What we recommend doing is holding the coffee filter up high and setting up the camera watching you. Watch the footage until the coffee filter reaches this point. Once it reaches that point, start the timer. Then stop the timer once it hits the ground. It is important that at this point, the coffee filter must have reached terminal velocity. It is important to not start the timer at the top because the coffee filter will not yet have reached terminal velocity. So make sure it's already reached terminal velocity by this point. Now, measure this distance that you started and stopped the timer. Then, that is the distance traveled. Also, the time that you measured is the time elapsed. From that, we can get velocity. And since we only measured it while the object was in free fall, that is your terminal velocity. Congratulations. Now, for this experiment, we are going to have to measure different things. We're going to vary the mass as one of them. And for the simplicity's sake, we are going to take each mass equal to 1 gram. So each coffee filter equal to 1 gram. If you add another coffee filter, that's going to be 2 grams, and etc. You see where this is going. Now, also, you're going to be varying the cross-sectional area of the coffee filter. From that, if you don't know how to calculate cross-sectional area, is area equals pi times r squared. So what you would do is measure the diameter of the coffee filter, insert that in the equation, you get area is equal to 1/4 pi times the diameter squared. Now, this is the equation for terminal velocity, for the, for drag force. This is equal to 1/2 times the drag coefficient times rho times the area, cross-sectional area that is, times the terminal velocity squared. For this experiment, the drag coefficient is dependent on the shape of the coffee filter. They're basically all shaped the same way. That will be a constant throughout this experiment. Rho is going to be the density of the air, assuming you are dropping the coffee filter in the same air with each trial. That is also going to be a constant. So your only variables are going to be the cross-sectional area and the terminal velocity squared. From this, you can solve for a terminal velocity to get this. Now, from this equation, the acceleration due to gravity here, that is also a constant. So, the only variables are mass and the cross-sectional area. The first time, you will be varying the different masses, and so from that, you are keeping the area constant. Thus, the terminal velocity is dependent only on mass. All of this is a constant. These are your two variables. Then you will be varying the area. How will I vary the area, you might ask? Well, simple. You can simply cut around the coffee filter to change the cross-sectional area that you measure. Then, you are keeping the mass constant. So the number of coffee filters will stay constant in this calculation. And now, your only variables are terminal velocity and the cross-sectional area. That should be everything. If you have any more questions, please feel free to join the LA office hours. Those hours are listed on the D2L homepage, and good luck.